Greetings and welcome back. This is section 15. This is the N1IR element 2 question. So we're going to go with electrons go with the flow. Okay, we're almost there. We are on section 15. Okay, the electrical term for the electromotive force, EMF, that causes electron flow is voltage. So EMF is voltage, electromotive force. The basic unit of electromotive force is voltage. The instrument used to measure electrical potential electromotive force is a voltmeter. So we call it voltage. We're measuring with a voltmeter, and the volt was discovered by Alexander Voltaire. It was named after him. And he experimented a lot with DC batteries. So the volt is named after him, Voltaire. And you'll see voltage, voltmeter. So EMF is voltage. And to measure voltage, you measure with a voltmeter. The correct way to connect a voltmeter in a circuit is in parallel with the circuit. So later on, I'm going to get into an ammeter. And that one goes in series with the circuit. So the voltmeter goes in parallel and the ammeter goes in series with the circuit. And you want to be careful not to confuse the two if you're actually measuring stuff. If you accidentally use an ammeter to measure a battery voltage, you're going to see some smoke. So just keep that in mind. Voltage is measured in parallel with the circuit. Okay, types of batteries that are rechargeable. Okay, so you got nickel metal hydride. You have lithium ion. You have lead acid gel cells. All these choices are correct. So you got some of the older technologies such as NiCad, nickel cadmium. There's also lithium polymers, and there's this new Fe battery too. The iron type batteries that are rechargeable. Some of the newer technologies that are out there. So, but in the test, they have nickel metal hydride, lithium ion, and lead acid gel cells. Those are the most common ones that you see out there right now. This type of battery is not rechargeable, carbon zinc. So this is the carbon zinc ones is still what you'll see at like the dollar store. Those are like carbon zinc. A mobile transceiver usually requires 12 volts. It's cars are 12 volts nominal for voltage. The negative return connection for a mobile transceiver power cable should be connected to the battery or the engine block ground strap. So we want to have a good ground. You want to have either a good ground to the battery or to the engine block ground strap. I like to go directly to the battery, and I like to fuse the negative side just in case the engine block ground strap fails. If I'm connected directly to the battery, my wire isn't going to be the path to ground and cook that wire, because that wire that I have on my radios is only like 12 gauge, and if that ground strap does go in the engine block, you'll have hundreds of amps when you start it. So that's why you want to fuse your negative and your positive. That negative one is just in case you have a ground loop in there. The name for flow of electrons in electric circuits is current, and that's measured in amps. The instrument used to measure electric current is ammeter, and again, this was named after Ampere. An ammeter is usually connected to a circuit in series with the circuit. So as I mentioned before, you want your ammeter in series and your voltmeter in parallel. Electrical current is measured in amperes. Copper is a good electrical conductor. The name for current that reverses direction on a regular basis is called AC. So AC goes a positive direction and a negative direction. We've been talking about DC, which goes one direction only. So AC is alternating, DC is direct current. The device or circuit that changes an alternating current to a varying direct current signal is a rectifier, and that's usually can be up to from 2 to 4 diodes for a single phase AC. So you'll see either 1, 2, or 4 diodes being used as a rectifier to convert the AC into DC in your power supply. The name of the current that flows in only one direction is called direct current. So there's two types of current flows that are out there. There's conventional current flow, which flows from positive to negative, and there's electron current flow, which goes from negative to positive. Now, which one is correct? We still don't know to this day which one's correct, which way the current is flowing. But the conventional current flow is usually used in science books, and electron current flow is usually with electronic engineering manuals and books. So you'll see conventional and electron flow, and that's the difference between the two. And again, it's all theory. We don't know which way it goes. So here's some different types of batteries. So you got the 9-volt battery. Here's a AAA. That's actually a AA battery. That's not a AAA battery. Motorcycle battery. That's a lead acid. And a handheld battery. That looks like a lithium. Okay, the electronic component that allows current to flow in one direction is the diode. So the diode is kind of like a one-way street. It only allows current in one direction. There are two electrodes on a diode. One's called the anode, and the other one is the cathode. The cathode lead of the semiconductor is usually identified with a stripe. So here is a diode schematic symbol. Here's the schematic symbol of the diode. Current will flow only one direction. You can remember this by the diagram as a one-way arrow. So if you think of conventional current flow from positive to negative, that is true. It goes in flow with the arrow. If you're using electron flow from negative to positive, it doesn't look right. So these symbols were created when conventional current flow was the norm. This one is a Zener diode. You can notice the little angles here, and that indicates that it's a Zener diode. Now, a Zener diode regulates voltage. It's a voltage regulator, and it's typically reverse biased. The electrical component that's used to oppose flow of current in DC is called a resistor. And when the current flows through the resistor, it dissipates that current as heat, changes that current into heat. The instrument used to measure resistance is called the ohm meter. Again, ohm was named after George Simon Ohm. So he was the one that discovered resistance, and he did a bunch of experiments with resistance. The component often used as an adjustable volume control is called a potentiometer, or a pot. The electrical parameter that's controlled by a potentiometer is resistance. So a pot is just a variable resistor. You actually, let's see, a good electrical insulator is glass. So glass, plastic, ceramic, those are all good electrical insulators. Electrical component that stores energy in a magnetic field is an inductor. So a coil of wire is an inductor. So it's going to store that energy in a magnetic field. And if you ever took some enamel wire and wrapped it around a nail and made an electromagnet, you'll see that that energy is stored in the magnetic field. The electrical component, usually composed of a coil wire, is an inductor. So the electrical component, usually composed of a coil of wire, is an inductor. So a coil of wire is an inductor. So the ability to store energy in a magnetic field is called inductance. The basic unit inductance is the Henry, again named after the scientist that has discovered the inductor. Impedance is measure of the opposition to AC current flow in a circuit. So when we talk about impedance, we're talking about AC resistance, and it's a little bit different than DC resistance. You'll have impedance with inductors and capacitors. They'll have an AC resistor component depending on frequency, the dynamic. The unit of impedance is the ohm. The ability to store energy in an electric field is called capacitance. So this is an electrostatic field. They have it as electric field, but it's actually electrostatic field. And it's basically stored between two plates and an insulator for the capacitor. The basic unit of capacitance is the farad, again named after one of the scientists that has discovered capacitors. The electrical component that stores energy in an electric field is a capacitor. I would again change that to electrostatic field. Alright, so here is a construction of a capacitor. So this is the basic construction. You have your two leads, and you have plates, and you have a dielectric or an insulator. So that could be paper, it could be mylar, anything like that. It could be ceramic or paper. Here's paper one. So this is metal foil with paper, and they roll it up, and that's a schematic symbol. You have a line and a curved line. This is a polarized capacitor. So this side is positive on the top, and the one line with the curved line is the negative. Now if it wasn't polarized, you would have two flat lines. Okay, the electrical component that is used to connect or disconnect the electrical circuit is the switch. The electrical component that's used to protect other circuit components from current overload is a fuse. So I highly recommend using fuses in all your gear. It's cheap insurance, right? And please do not bypass fuses with aluminum foil or 22 gauge rounds or anything like that. You know, your fuses are cheap. Use them, please. Please use them. They're a safety device. Okay, the component that can be used as an electronic switch or amplifier is a transistor. So a transistor can either be operated in the linear mode, or it can be either cut off or saturation, on or off, like a switch. Class of electronic components that are capable of using voltage or current signals to control current flow is a transistor. So a transistor is kind of like a potentiometer that is controlled by a current source. You can think of it that way. If you have a small amount of current, it controls a larger current. Transistors are current-controlled devices. Transistors is an electronic component that can amplify signals. So this isn't using the transistor in the linear region. You can amplify. You can take a small amount of current and it can amplify to a larger amount of current. The term that describes a transistor's ability to amplify a signal is gain. 3 electrodes of the PNP NPN transistors are the base emitter and collector. So the NPN on the left here, the arrow is not pointing in, NPN, not pointing in. And the arrow is always the emitter lead. And you can see where the line is, that is the base. And the opposite to the emitter is the collector. So NPN and PNP, the NPN you can identify as the arrow is not pointing in, and the PNP, the arrow is pointing towards the base. The components made up of 3 layers of semiconductor material is the transistor. So you got 3 layers, an N material, a P material, and an N material for the NPN, a P material, an N material, and a P material for the PNP. The FET. FET stands for Field Effect Transistor, FET. And these are junction FETs, and we have 3 leads on these as well: gate, source, drain. And they have conventional current here, so that's the conventional current flow. So the N channel, the arrow is pointing towards the source. The P channel, the arrow is facing away from the source and towards the gate. Now these are a voltage control device, and this is called depletion mode. So these guys, unlike the transistors, transistors are off, usually off, a normally off device until you bring a current to the base, and then it turns on. These are kind of opposite. They're on until you bring a voltage over to the gate, and then it shuts it off. So you can think of these are like a garden hose, and you come over and you crimp the garden hose. That is the gate voltage, you crimping that hose and limiting the current. So this is almost like a normally on device until you bring that gate voltage, and the transistor is a normally off until you bring a small amount of current onto the base. So that's the difference between the FET and the transistor. BJT transistor, bipolar junction transistor. The three electrodes of the FET are the source, gate, and drain. Now, when you hook it up in a circuit, you can pretty much interchange source and drain. There is a little bit of a difference, but you can flip those two around. Unlike the transistor, the emitter has to go in a certain place, the collector has to go in a certain place. The source and drain you can kind of flip, and there's going to be a small change, but not too much. So these work in both directions, which is pretty cool. Okay, so now we're going to go on to the Q&A section of Electrons Go with the Flow.